Right. Yep. Yep. A lot to do. Okay. So what exactly is interference? So interference is when two or more waves combine to form a new wave. That's firstly the meaning of the word interference. And, you got that? Yeah? And the principle of superposition states, now I wonder if any of you have heard that principle before. No? It states that the net amplitude of the new wave at each point is the sum of the amplitudes of the individual wave. Now before you continue writing that down, I just want to explain that simply. So if you look here, let's imagine you have one wave here, goes like this, and then you add that to another wave. The waves, they come together maybe. So maybe this wave goes like that. Then you'll get this wave. Because the rule is, like let's say at time t here, time t, I can't quite see it, time t here, this one has a height h1, this one has a height h2, so the height at this point would be h1 plus h2. That's the principle of superposition. It's like an algebra rule. Just says the new height is the sum of the two heights. That's all. Principle of superposition.
So
yeah.
One.
So for example, let's say here the height was 1 meter and here the height was 1 centimeter. Then here the height would be 1.01 meters.
So there are two vibrations, like.
Yeah, two waves, like two sound waves.
And at the same time.
Yeah. So I'll give you a clearer example. Sorry. Let's say I have this wave here, and then let's say I have this wave here. Okay, so let's try and visualize what we would get here if I was to add them. So here, this wave, they both start to increase in height. So it'll get quite high. And then at this point here, it's still high. But then what happens is this one starts to decrease. But this one is still increasing. So I think it might kind of maybe do a little bit of cancelling and then maybe kind of flatten out a bit. Maybe. But then here, this goes down and then this starts to go down. So they both go down like that. So I think maybe we'll get kind of a wave that looks like this. I don't know. Let me show you with a graphing program. Close this. I'll graph one for you. I think I might have a picture. Yeah, here's a picture, but I'll make a graph for you too. Can you visualize the two coming together? You want to take a picture?
Yes.
I want to show you a graph here. Oh, come on. Steady. No, not yet.
How old is your PC?
Old.
Older than Diego's?
Sin x. Right, can you see? Can you see that okay?
Yeah.
And then I'll do a sine 2x wave. There we go. Looks like that. Okay, now let's add them together. So I'm going to delete this picture. I'm trying to redraw the picture I had here of the two waves. Okay, so delete. Alright, let's see what we get. Ready? Okay, I was way off. I was way off. That's what it looks like when they combine the two of them. Yeah?
So it has a big increase and then like, whoop.
Yeah. Interesting. Okay, I'll do one more for you. I'll do like the first one I had. I'll do sin x, which looks like that, and then 0.1 sin x, which looks like that. Actually, you know what? I'll change a little bit. I'll do 4x here. Okay, so have a look. That one. That one. Add them together. Let's see what we get. So I hope it's like the picture I drew. There you go. Can you see it in black?
Oh yes.
Yeah, okay.
Yeah.
So if it's like sin x and cos x, just gets a flat line.
Yeah, you're right. That's what we're going to look at in a moment. If you had something like, let's say cos x, and then I'll draw this one. Oh, maybe not quite sine and cos. Sine x and minus sine x, they would cancel then, yeah. Let's see what we get if we add these together. 1 and 4.
If you add that.
I don't know, we're not, no, not tan. Right, so I think we'll get a wave that the blue one wants to go up, but the red one wants to go down. So I think it'll be kind of flat at the start. Let's see. I know, it's
What?
way off, huh?
What?
Yeah, that's surprising. Let's put the two together. Weird, huh? Let's put the originals back in.
Oh, it does get really.
There's sine. There's cos. And then there's sine plus cos. Yeah, okay, yeah. Right, so sometimes it's not obvious how they combine. I think this picture's an easy one. That was the first one I did. You have a big wave, and then you have a little fluctuating wave. Now, what I would like you to do is obviously the definition and this diagram.
Damn it, I wrote the principle of superstition.
I know.
Superstition. When is Chinese New Year?
Tomorrow.
It's tomorrow.
Today is.
It's Eve.
Today
Huh?
is the Chinese New Year's Eve.
Yeah, okay. So you have a party tonight or tomorrow?
Tomorrow.
Tomorrow.
Kind of. We're just going to the festival.
Oh, good.
And then
Good.
having dinner. Do you know about the festival? Have you seen?
No, no. I don't know, I've never been to the festival.
Fiona mentioned it, and you're like, yeah, we're all going to the whole class.
Hmm.
Oh yeah.
He's going tomorrow.
No, it was just
You like
thinking that
Chinese food and details.
they have a lot
Like
of
street
really
food and
interesting things.
Yeah, no, I imagine.
Well, not like interesting as in bad, but like
Oh, okay.
it's like I think everyone will enjoy the candy art. Like they make art with the candy.
Oh, nice.
things that I bought
You can eat it
of
or keep it.
No, actually, this ones. Like you put them inside. They have to do that. You know the chrono disease? That's the great.
Which one?
The chrono disease. No, that was already.
I've heard of it, but I really don't know much about it.
The one.
What?
Yeah, the chrono disease.
Oh,
Yeah,
They were
I saw that
2
they're
years.
testing some people
Yeah.
here in Belfast, I think.
Yes, there's one case in Belfast and one in Singapore.
Okay.
Yeah.
Right, have you got this drawn and written down? Now, I think Dorian and maybe Zach as well, you notice that you might be able to put the waves together so that they cancel. Yeah, that's an important idea too. Can I continue?
Yes.
Yeah. Now, before we continue, the definition: two wave sources are coherent if they have a constant phase difference. Do you remember phase difference?
Yeah.
The distance between the peaks of the two waves, and the same wavelength. Now, actually, I'm sorry, I need to check that because I was wondering recently if it's the same wavelength or the same frequency. So I just want to double check that for you. So don't write down wavelength, just write the same and leave it blank for a moment. Yes. So it is the same frequency, not the same wavelength. Now, that doesn't matter too much because often we're looking at light waves in a vacuum.
So it's the same?
Same frequency, it should say, sorry. So I'm going to just, I'll have to fix that here. So when you write this down, did you all write down frequency instead of wavelength?
Okay.
Alright, and here's an example picture here. You can see the phase difference. So here's the crest of the first wave, and here's the crest of the second wave, and there's their difference. Crest, crest, difference, crest, crest, difference. That distance is constant, so that's the first part, constant phase difference. Now, I said the frequency is the same. Because these are both light waves, and you have the formula C equals, lambda equals C over F. Having the same F here means having the same wavelength. Do you know what I'm saying? If you say, if you're saying F1 equals F2, and F equals C over lambda, then really you're also saying lambda 1 equals lambda 2 in this picture, because they're both light in a vacuum. Okay, but technically it's the same frequency. All right. It would be great if you could add this picture to the definition, but let me just recompile my notes. Okay. So if you can copy this picture, please. Oops, sorry. Sorry, I'm reopening it. Now, you got that? You got that, guys? Now there is, for coherence, a third requirement. They're the same phase difference and the same frequency. The third requirement they don't need for the exam. But I just want to tell you about it. You actually need constant phase difference, same frequency, and the same waveform. I actually have a picture here. I'll show you guys. Can you see here? Gina? And I'll come back to you. The waveform is the shape. So on this course we only study this waveform. But if you were doing engineering, you can study the other waveforms in electrical signals. Okay. So I don't know, did you see that okay then? Oh. Oops. Come on. There we go. This is called the waveform. So we only study this waveform, but not the square of triangles. Yeah. If you study engineering, you'll study these waves. Can you see them, Zach? Yeah. Yeah. This second one is I think they call it a clock waveform, because it's like a clock, up, on, off, on, off, on, off. You know. This one is called a sawtooth waveform, because it's like a saw. And I don't know what the last one is. Oh, I'm sorry. That one's called triangle, and the last one was called sawtooth. Anyways, it doesn't matter. We only study this type. What name would you describe this shape, by the way? What type of shape is that? This type of shape, what would you call it?
Like
An uppy, downy shape? Like, what would you call it? Give me an adjective.
like an adjective.
Yeah, give me an adjective to describe this shape.
Bumpy.
A bumpy wave. Let's make it a bit more formal.
So we have a hint.
Begins with, it's a word you know from maths class. There's a noun in maths class that you can turn into an adjective. So where have you seen these graphs before?
Sin, cos, tan.
Yeah.
Metric.
Yeah, we're not quite trigonometric. Let me just get the... It's sine, isn't it? But you need to change sine into an adjective. Sine is a noun. Sine curve, you know, the sine curve or whatever. That's
Sine.
like sine function. That's a noun. But you want to describe this as the sine wave, but you need to make it an adjective. So what's the adjective form of sine?
Sinus.
A siny wave. A sinus wave. I like it. Sinus wave. I'll write it down if you don't know it. Oops. Nobody wants to have a guess? I like sinus and siny and sinely. Sine is the noun. Santi? No.
Sinusoidal.
I also was right.
I don't think. Yeah, okay. That's the adjective.
Sinusoid. Is that, I don't know.
Sinusoidal, yeah.
Sounds like sinus and suicidal.
Oh, yeah. Okay. Yeah, there's quite a different form from the noun. So this is what you call the wave form. New word? Or did you know this word? It's new? Yeah? For you as well, Zach? Yeah. Okay. Continue. When two coherent waves propagate together from two different sources and they meet, then we say the path difference is the difference in the wavelength each wave travelled. And we express this usually in the form of k lambda. Now, that picture isn't super clear. I think I'll just draw it and then I'll let you write the definition down. So let's say you have source 1, source 2, and here's where they meet. And here's the first wave. We have one wavelength, maybe two wavelengths, and then maybe half a wavelength. Okay? And then this one here, maybe we have one wave, and then maybe we have two waves. Now, how far did the first one travel? It travelled 2.5 wavelengths. And how far did the second one travel? 2 wavelengths. So we say the path difference is half a wavelength in this example. That's what we mean when we say path difference. And that's actually very important, because what would happen is, suppose this one travels 1, 2.5, and suppose this one travels 1, 2.5. When they both meet, they're both meeting at their crests, right? The first wave goes up.
Would be 2.25.
Oh, sorry, I said 2.5, didn't I? I'm sorry. Yeah. Say the first one is 2.25 and the second one is 2.25. Then they both meet when they're at their crest. So, according to the principle of superposition,
1.25.
oh, sorry, the other, well, okay, whatever. Yeah, the other one's 1.25. Still, when they both meet with their crest. So what does the principle of superposition tell us?
Don't they have to be parallel in the same?
No.
They add together.
They add together. So for example, let's say the first one had an amplitude of 1 meter and the other one had an amplitude of 1 meter. Then when they meet, they cause an amplitude of 2 meters. Yeah. But what would happen if it was like this? So this one finishes on a trough and this one finishes on a crest. What would happen at this point?
They equalize.
Cancel.
They cancel, yeah. Now this is actually how your, if you still have one, CD player works.
Oh,
You know your CD player?
yeah.
CD player? Do you still have those, kids?
I do.
Yeah. So you know when you look at the CD, the surface looks like this.
Mm.
You know, it has up, down, up, down, up, down. And then you have your red laser, and then you have here this detects. So what happens is, and then you have, I think then you have another laser slightly off-centered here. So this goes up, down, well hang on, try that again, Stephen. Okay. Up, down, center, up, down, center. Oh man, sorry, this is looking bad.
You can draw it.
Up, down, okay, I'm sorry. I want this to finish on a crest, okay? And then this one comes along and it also finishes on a crest. So what happens to the two crests? They add together. So you have a very strong wave that comes back here. Now, when it gets to this one, sorry, I'm not drawing it great, but when it hits in here, this length is designed so that a crest and a trough will meet. So what happens when a crest and a trough will meet? They cancel. So then there's no light that is reflected. Do you understand? So the way they design the CD is that they make sure that this distance is half a wavelength. So, because you notice that if you have a wave and you move it by half, so let me draw it in blue, what happens if you add these two waves together? They cancel. So on the CD, you need this distance to be half a wavelength, and then you can have this effect, where if you shine it on a peak, on a top, it reflects, but if you shine it into a hole, no reflection. So then the computer here, if it gets a light, it gets a 1, and if it gets no light, then it gets a 0. And then you get the information. Okay.
That's why if you scratch them.
Yeah, if you scratch it. So if you scratch it and you break the top off, then you've lost that You've lost that information.
CDs with?
Huh?
How do rewritable CDs with?
Yeah, I think what they do is there's a layer on top. So it's almost like this. There's some layer on top, and then the CD burns the top off. And then if you need to rewrite it, it'll burn the whole top off and then start a fresh layer. That's why these have a limit, maybe of 1,000 rewrites, because eventually there'll be nothing left to burn.
So that's also how hard drives work.
No, hard drives totally different. They use magnets instead, and we can actually talk about that in the atoms then. Yeah. So
How does solid state memory work?
I don't know. I have to look into that.
Yeah, that's what I mean, like the ones that spin.
Yeah.
That are like a small CD.
The mechanical ones.
You know, like you have the SSDs.
I
and
know
the-
how I know how my one works. The old HDD.
Yeah.
Yeah,
But I'm not sure about what's it SSD.
Yeah,
I don't know how that
solid
works.
state,
Yeah, I don't know. I'm not sure, and I don't know about SD cards either.
I think
because an
it's
SSD is
flash
actually a big SD card.
That's what I thought. Yeah. Can you write that definition down and try to draw some kind of picture? No, it's okay. You don't have to draw a picture, but at least write the definition down. So, what's the most important path difference? The most important path difference is half a wavelength, because we have a cancelling effect then.
Different sources.
From two different sources. Me speak English. Yes, thank you, Diego. Should be two different sources.
In the Spanish guy could say
Look, man, typos happen.
What are you trying to say about that? Maybe racist or something.
Huh? Zach's racist? I didn't know that.
Yeah.
When did this start, Zach? When you met Diego?
must be.
I was that technical things.
What? Okay, you got that? No?
What is the name of K?
Oh, it doesn't have a name. I'm just trying to make it clear that we usually express the path difference as a multiple or a fraction of the wavelength, yeah.
K
Because
is
it's
a-
more meaningful that way.
So K is a fraction.
So when you say K is half, what do you mean?
Yeah, like half, for example.
So
K could be half. That would be
cancel
a cancelling effect. Yeah?
You have to draw it.
No, you don't have to draw it if your definition is good enough. Right, have you got that? Yeah? Now, before you go, we'll look at this next time, but you could probably figure this out. Waves can add together. and we actually call that constructive. And they can cancel each other, and we call that destructive. And then completely destructive, what would that mean? Yeah, completely cancel each other out. So here is completely constructive and completely destructive. Now we look at this next time. I'll continue with this next time. But just before you go, can any of you think of an example where you have this in real life? Not quite, well, depends.
When in real life?
Yeah,
when you try to skip rope, but then
No. When you put on your headphones. Your headphones have noise cancelling technology in them.
Well,
What your headphones are doing, or at least trying to do, is to produce a second wave that will cancel the incoming wave you don't want.
so he analyzes the waves that come in
Yeah,
and then produces.
exactly. It produces a cancelling wave that will play in the speaker.
So all those speakers, like all those headphones, have a small microphone. Yeah.
Correct. Yeah. Now, it's easier to cancel waves that are repetitive. So if you were on a train and the background of the train is going, it's very easy for the computer to cancel this wave. But me talking is very difficult for it, because if you were to look at my sound wave, it's changing a lot. And the computer cannot quickly enough produce a cancelling wave for this. So this is why your headphones work really well on the bus or the train. I use them on the train, and it works really well to cancel the train engine, because the train engine is just going, so it really cancels it. But when people start talking, I can still hear them slightly, you know. Yeah, so I think this is all interesting stuff. We'll continue with this slide next time though, okay? Do you all have noise cancelling headphones? No? I thought you have fancy Sony ones.
yeah, I do.
Yeah, you do, yeah.
I like this.
They work well?
You want to try it?
Yeah, come on, I'll give it a try. Do you need to play something for it to work?
Well, it doesn't. Well, you can immediately
Yeah, some of
cancel
them
it
are
out.
active and some of them are passive.
You can immediately feel it. So you put it like this,
Yeah?
and then you press this button. You
Okay.
just press it until there's a sound, and then you
Huh?
can feel
Press which button?
this power button.
Oh, okay, it's off now, is it?
Yeah,
Is this right?
like this. This side.
This way.
Yeah.
Power button on the left.
Yeah. So you can see when it turns on, you can feel a little bit of the noise. Cancel. You have to press it longer.
Oh.
Until there's a sound. Like
Until I
press.
hear a beep, yeah.
Yeah.
But then we have to kind of examples.
Now you're going to pretend not to talk, is it?
No, but you have to at least hear something.
Yeah.
Is it connected to my? Okay.
Are you talking at normal volume?
Yeah, he's talking normal volume. No, he's not, but he is.
Yeah, okay. Okay, yeah. I got noise cancelling headphones, but I didn't get fancy Sony ones. How much are those Sony ones? Are they 200? 300?
Euros?
Those ones?
I don't know. Wait, how much is yen to euro?
M3 something.
No, it's WH. Something. Oh, how much is?
My one.
No, it's this one.
No,
The
WH.
Sennheiser ones are really good.
And they're really pricey.
Yeah.
To euros. Let's see.
You also have the,
0.0083.
Bose.
Yeah, but these are expensive, man, you know. We're talking teacher salary here.
Hartman also.
Yeah.
Less than 100 euros.
Beats are not.
99.6 euros.
Okay. I spent 60 on mine. It's kind of my budget. No, that's good. And they're very comfortable.
They are
Very
nice as well.
Yeah. Yes.
Also, there's like Bluetooth touch sensor.
You think I don't
Bluetooth
like about
touch?
those?
So if you put it like this, it's Bluetooth. So I don't have to touch my phone. I can switch the songs just from
Yeah.
the touch panel. Yeah. Touch sensor.
Oh, so there's some
You
control you have by finger movements on the surface.
Yeah, and if you like don't want to take it off, I want to hear it or just press on it, they cancel out everything and you can hear the person talk and they amplify the sounds from outside.
They amplify the sound. Wow, this is fancy.
You scream to them.
Yeah.
I mean, yeah, but like as in if you just put it on, there's still some blockage. But then when you put like this ambient, they turn into ambient sound, and you can hear everything.
Oh, fancy.
People are thinking that you don't
Fancy.
listen to them and you're like.
You're like this, you can hear
Well,
everything.
look, guys, my birthday is in June. If you want to buy me one, you can split the cost between you.
I don't
Mine
know.
is in April, so.
Wait,
earlier.
our class is funny. Like, who's April 5th, April 15th, and April 25th?
Who's April 25th?
25th.
Ah, and you're 15?
I'm 15.
And then Harry's 15th.
Oh, it's a few April people then.
5, 15, 25.
5
Yeah.
to 15, 25.
Wow.
All right, next week, isn't it? So, you're probably all going to be busy working on your chemistry lab report, huh?
Yeah.
Now and maths and English.
Oh yes, you have the coursework, don't you?
In
I haven't
English.
started maths.